A mysterious blue glow appeared in the Sun's corona on the 2nd day of November, 2025, and nobody could explain it. Scientists monitoring our star through various space telescopes noticed something that shouldn't be there, a faint luminescence in wavelengths that didn't match any known solar phenomenon. The timing was impossible to ignore. At that exact moment, 3I Atlas, the massive interstellar visitor that had been puzzling astronomers for months, was making its closest approach to the Sun on the far side from Earth. Parker Solar Probe, humanity's closest eye on our star, captured the first clear images. The spacecraft's wide-field imager revealed unusual emissions surrounding the expected position of the comet. But this wasn't the typical dusty halo that astronomers associate with comets passing near the Sun. Instead, the light appeared concentrated, almost structured, glowing in shades of blue and violet that stood out against the Sun's normal corona. The phenomenon defied immediate explanation. Solar physicists knew the corona well, having studied it for decades. They understood the physics of how million-degree plasma behaves, how magnetic field lines twist and snap, how solar wind streams outward at hundreds of kilometers per second. Yet nothing in their models predicted a blue glow appearing exactly where an interstellar object happened to be passing. Teams at NASA's Solar Dynamics Observatory cross-referenced their data with Parker's observations. The correlation was undeniable. The blue light tracked with 3I Atlas's trajectory through the most intense radiation environment in the solar system. As the object moved through its perihelion passage, the glow moved with it, maintaining a consistent relationship to the comet's position, even as both hurtled through space at tremendous velocities. European observers using ground-based coronagraphs added their own confirmations. Despite observing from Earth's surface, looking through our turbulent atmosphere and fighting the overwhelming glare of our nearest star, multiple facilities detected the same anomalous emissions. This wasn't an instrumental artifact or a processing error. Something real was happening in the space around 3I Atlas. Something that made it visible in ways that violated every expectation about how comets should behave near the Sun. The spectroscopic signature added another layer of mystery. When astronomers split the blue light into its component wavelengths, they found emission lines that didn't quite match the catalogue of known solar emissions. Some wavelengths suggested highly ionized metals. Others hinted at molecular fragments that shouldn't survive the intense heat near the Sun. A few lines remained completely unidentified, their origins unknown to even the most experienced solar spectroscopists. As word spread through the astronomical community, researchers scrambled to point every available instrument at the phenomenon. They had, perhaps, weeks before 3I Atlas emerged from behind the Sun into Earth's view. Whatever was causing this blue glow, it was offering a window into physics that nobody had witnessed before. Parker Solar Probe had been built to withstand hell. Launched in 2018, the spacecraft was designed to dive closer to the Sun than any human-made object before it. Protected by a carbon composite shield that could endure temperatures exceeding 1,300 degrees Celsius. By late 2025, it had completed multiple close approaches, sending back unprecedented data about the solar corona, solar wind, and the Sun's magnetic environment. But nothing in its 7-year mission had prepared its operators for what the wide-field imager captured on the 2nd day of November 2025. The WISPER camera, short for Wide Field Imager for solar probe, was designed to photograph the Sun's outer atmosphere and track structures in the solar wind. It operated in visible light wavelengths, capturing images that looked somewhat like what human eyes might see if they could somehow survive near the Sun. On this particular orbital pass, WISPER was pointed at a region of the corona where 3I Atlas was expected to be making its perihelion passage, though nobody expected to actually see the comet itself through the overwhelming brightness of the solar environment. What appeared in the images shocked the mission science team. A distinct blue-tinted glow had emerged in multiple consecutive frames, persisting across several hours of observation. The emission appeared concentrated in a region roughly matching where orbital calculations placed 3I Atlas. At first, scientists suspected an instrumental problem. Space is harsh on electronics, and cosmic rays regularly create false signals in detector arrays. Perhaps a charged particle had struck the camera sensor at just the wrong moment, creating an artifact that mimicked a real astronomical source. But the glow appeared in frame after frame, maintaining consistent brightness and position relative to the background stars. It moved across the field of view at exactly the rate expected for an object following 3I Atlas's calculated trajectory. The team ran diagnostic checks on WISPER's systems. Everything functioned normally. They examined calibration data from before and after the observation. The camera was working perfectly. They processed the images using different techniques, trying to make the blue glow disappear into noise or reveal itself as a processing artifact. It remained stubbornly present in every analysis. The wavelength distribution of the light added to the mystery. WISPER's filters allowed scientists to determine that the blue glow peaked in wavelengths around 450 to 500 nanometers, firmly in the blue-green portion of the visible spectrum. This was unusual because most comet activity near the Sun produces emissions in the ultraviolet, or appears as white, scattered sunlight from dust grains. Pure blue emission suggested some kind of fluorescence or plasma process that wasn't part of the standard comet playbook. Mission scientists immediately contacted colleagues operating other solar observatories. If this was real, other instruments should see it too. The search for independent confirmation had begun. The Solar and Heliospheric Observatory had been watching the Sun continuously since 1996, making it one of the longest-serving spacecraft in the history of solar physics. Positioned at a gravitationally stable point between Earth and the Sun, SOHO carried 12 different instruments designed to study everything from the Sun's interior vibrations to the acceleration of the solar wind. Its coronagraphs, which block out the Sun's bright disk to reveal the faint corona, had discovered over 5,000 comets during nearly 3 decades of operation. None of them had ever produced anything like what appeared on the 2nd day of November, 2025. SOHO's LASCO C3 coronagraph, designed to observe the outer corona from about 2.5 to 32 solar radii, captured its own images of the blue anomaly completely independently of Parker Solar Probe. The spacecraft operated on a different orbit, used different instruments with different sensitivities and wavelength responses, and processed its data through entirely separate computer systems. Yet, when scientists compared timestamps, the correlation was unmistakable. SOHO detected unusual blue-shifted emissions in its field of view at precisely the same time Parker's WISPER camera recorded the mysterious glow. the independent confirmation eliminated any remaining doubt that this was merely an instrumental glitch. Two spacecraft, built by different agencies decades apart, using completely different detector technologies, had both captured the same phenomenon. The blue light was real, and it was definitely associated with 3I Atlas's passage through the inner solar system. SOHO's observations added crucial details that Parker's closer view couldn't provide. The coronagraph images revealed that the blue glow extended much farther from the comet's nucleus than initial estimates suggested. What appeared as a concentrated emission in Parker's wide-field imager actually formed part of a larger structure, an elongated envelope of glowing material that stretched for hundreds of thousands of kilometers along 3I Atlas's orbital path. The emission wasn't uniform either. It appeared brighter on the sunward side of the comet's position, creating an asymmetric pattern that suggested directional processes, rather than simple spherical expansion. The spectroscopic capabilities of SOHO's instruments provided additional insights. The spacecraft's ultraviolet coronagraph spectrometer detected emission lines that matched ionized carbon, oxygen, and nitrogen, along with several unidentified features in the blue portion of the spectrum. These signatures indicated that 3I Atlas's coma was undergoing extreme ionization in the intense radiation environment near the Sun. But the specific combination of emissions, and particularly their brightness in visible wavelengths, didn't match the standard models for how cometary material behaves when heated by solar radiation. Ground-based observers received the news from both Parker and SOHO teams with a mixture of excitement and urgency. Multiple spacecraft had now documented something unprecedented. The question shifted from whether the blue glow was real to what physical process could possibly explain it. Observatories around the world began preparing their own observation campaigns. Ground-based coronagraphs offered something that spacecraft couldn't provide: the ability to spread light into incredibly detailed spectra, revealing the exact wavelengths present in the blue glow. Within days of the initial Parker and SOHO detections, observatories equipped with specialized instruments began capturing their own data. The Mauna Kea Observatory in Hawaii, the Cerro Tololo facility in Chile, and the High Altitude Observatory in Colorado all turned their coronagraphs toward the region where 3I Atlas was making its closest approach to the Sun. What they found challenged fundamental assumptions about comet chemistry. Spectroscopy works by splitting light into its component colors, much like a prism creates a rainbow. But astronomical spectrographs go far beyond simple rainbows. They can detect thousands of individual wavelengths, with precision measured in fractions of a nanometer. Each chemical element and molecule emits light at specific characteristic wavelengths when heated or excited by radiation. By identifying these wavelength fingerprints, astronomers can determine exactly what a distant object is made of without ever touching it. The blue glow spectrum showed emission lines that didn't belong in the Sun's normal coronal spectrum. Several strong features appeared between 400 and 500 nanometers, the blue-green region of visible light. Some of these lines matched known transitions of ionized metals like iron and nickel, but they appeared far stronger than expected for typical cometary emissions. Other lines matched carbon monoxide and carbon dioxide molecules that had been stripped of electrons by intense ultraviolet radiation, transforming them into ions that could emit visible light. But the real puzzle came from three emission features that didn't match anything in the standard spectroscopic databases. These unidentified lines appeared at wavelengths of 462 nanometers, 478 nanometers, and 493 nanometers. Scientists combed through catalogues of atomic and molecular transitions, searching for anything that could produce emissions at these specific wavelengths. Laboratory databases, astronomical reference libraries, and theoretical calculations of exotic, molecular species all came up empty. Whatever was producing these three spectral lines, it represented chemistry that hadn't been documented before in astronomical observations. The intensity ratios between different emission lines provided additional clues about the physical conditions in three I-Atlas's immediate environment. The relative brightness of ionized carbon compared to neutral carbon suggested temperatures exceeding 50,000 degrees Kelvin in parts of the coma. The strong nickel emissions indicated that metallic atoms were being liberated from dust grains and excited to glow by solar ultraviolet radiation. The presence of both highly ionized species and relatively cool molecular fragments in the same spectrum suggested multiple distinct regions within the glowing envelope, each experiencing different heating and ionization conditions. The spectroscopic data transformed the blue glow from a mere visual curiosity into a complex chemical laboratory operating under extreme conditions. Scientists could now begin building models of what physical processes might create these specific emission signatures. But first, they needed to understand when exactly this phenomenon had appeared. When scientists plotted the appearance of the blue glow against three I-Atlas's calculated trajectory, the temporal correlation was striking enough to eliminate coincidence as a plausible explanation. The phenomenon didn't gradually build up over days or weeks as the interstellar visitor approached the Sun. Instead, it switched on with remarkable abruptness at a specific moment in time, precisely when orbital mechanics placed three I-Atlas at its closest point to our star. Astronomers worked backward through archived observations, searching for any hint of blue emissions before the 2nd day of November 2025. Parker Solar Probe had captured images of the expected region during its previous orbital pass in late October. Those earlier frames showed nothing unusual, just the normal coronal structures and solar wind features that the spacecraft routinely documented. SOHO's coronagraph data from the same period similarly revealed typical solar corona with no anomalous blue emissions. Whatever process created the glow, it required the extreme conditions that existed only during the closest approach itself. The timing precision was even more remarkable when scientists calculated three I-Atlas's exact distance from the Sun at various moments. The blue glow first appeared when the object reached approximately 0.3 astronomical units from the solar surface, roughly 45 million kilometers away. This distance placed three I-Atlas deep within what solar physicists call the region where solar radiation intensity becomes truly extreme. At this range, sunlight arrives with more than 10 times the intensity experienced at Earth's orbit, capable of heating surfaces to temperatures exceeding 1,000 degrees Celsius within minutes. But distance alone couldn't fully explain the sudden appearance. Several well-studied comets from the solar system had passed even closer to the Sun without producing comparable blue emissions. Comet Lovejoy survived a perihelion passage at just 0.8 solar radii in 2011, skimming through the Sun's outer corona itself. Yet, observations of that dramatic event showed only the expected white scattered light and ultraviolet emissions from standard cometary molecules. 3. I-Atlas was maintaining a much more comfortable distance, but somehow generating a completely different spectroscopic signature. The timeline also revealed that the blue glow didn't appear uniformly across 3 I-Atlas's entire coma. Sequential images from both Parker and SOHO showed the emission first emerging on the sunward hemisphere, the side facing directly toward our star and experiencing the most intense radiation. Over the following hours, the glow expanded and intensified, eventually enveloping a region hundreds of thousands of kilometers across. This progression suggested that solar radiation was triggering the phenomenon through direct interaction with material in the comet's extended atmosphere. Most tellingly, the blue light appeared to track 3 I-Atlas's motion with perfect fidelity. As the object moved along its hyperbolic trajectory, diving toward perihelion, and then beginning its outward journey back toward interstellar space, the glow moved with it, maintaining a fixed spatial relationship to the calculated nuclear position, even as both raced through the inner solar system at over 100 kilometers per second. Plasma physicists around the world faced a genuine puzzle when they tried to explain how an interstellar comet could generate visible blue light in the solar corona. The physics of comets near the Sun had been studied for centuries, and certain basic principles seemed inviolable. Comets were cold objects, collections of ice and dust that warmed gradually as they approached our star. They released neutral gas through sublimation, the direct conversion of ice to vapor without passing through a liquid phase. This gas expanded into space, forming the coma and tail structures that make comets visually distinctive. But this was all fundamentally cold physics, processes that involved temperatures of a few hundred degrees at most. Blue light emission required something entirely different. To make atoms and molecules glow in visible blue wavelengths, they needed to be excited to high energy states. This typically happened through one of several mechanisms, all of which required substantial energy input. Thermal emission from hot objects could produce blue light, but only at temperatures exceeding several thousand degrees. Fluorescence could create blue emissions when atoms absorbed high-energy ultraviolet photons and re-radiated that energy at longer wavelengths. Plasma processes involving ionized gas and strong electric fields could also generate blue emissions through various complex mechanisms. The problem was that none of these standard explanations fit comfortably with what scientists knew about comets. The neutral gas that sublimates from comet nuclei doesn't spontaneously heat to thousands of degrees. It expands and cools as it moves away from the solid surface. Solar ultraviolet radiation can break apart molecules and ionize atoms, but this typically produces ultraviolet emissions, not visible blue light. The spectroscopic signatures from 3 I-Atlas showed the blue glow came from highly energetic processes, yet the object itself was just a comet, not a miniature star. Theoretical models of comet-sun interactions had been refined over decades using observations of solar system comets. These models tracked how radiation heats the nuclear surface, how that heat drives sublimation of various ice species, how the released gas expands and interacts with solar wind, and how dust grains get carried along and eventually blown away by radiation pressure. Nowhere in these well-tested models was there room for the kind of energetic processes that could explain sustained blue emission over regions hundreds of thousands of kilometers across. The energy budget created additional problems. To maintain the observed brightness of the blue glow required continuous power input comparable to a modest solar flare. Yet 3I Atlas was supposedly just a passive object, warmed by sunlight, but not generating any energy of its own. Where was this enormous power coming from? Solar radiation alone seemed insufficient to drive the observed emissions unless some previously unknown efficiency mechanism was converting sunlight into blue fluorescence far more effectively than standard physics predicted. Some researchers proposed that 3I Atlas's unusual composition might hold the key. If the interstellar visitor carried exotic molecules or dust grain compositions never before encountered, perhaps these materials interacted with solar radiation in unexpected ways. Magnetometers aboard multiple spacecraft detected something unexpected in the days surrounding 3I Atlas's perihelion passage. The Sun's magnetic field, that invisible but powerful structure that extends billions of kilometers into space and shapes the flow of the solar wind, showed unusual perturbations that coincided precisely with the appearance of the blue glow. These disturbances weren't the routine fluctuations that scientists observe daily as the Sun's magnetic environment constantly evolves. Instead, they represented a distinct pattern that appeared to track with the interstellar visitor's position. Parker Solar Probe carried a sensitive magnetometer designed to measure the strength and direction of magnetic fields near the Sun with unprecedented precision. On the second day of November 2025, this instrument recorded sudden changes in the local magnetic field topology that lasted several hours. The field lines, which normally follow relatively smooth patterns dictated by the Sun's internal dynamo and coronal structures, showed sharp kinks and twists in the region where 3I Atlas was passing. It was as if the interstellar object was somehow pulling or pushing on the magnetic field, creating distortions that propagated outward through the surrounding space. The Solar Orbiter spacecraft, positioned at a different location along its own path around the Sun, detected complementary signatures. Its magnetometer showed waves rippling through the interplanetary magnetic field, traveling outward from the Sun at speeds characteristic of Alphen waves, magnetic disturbances that propagate through plasma, like sound waves move through air. The timing and direction of these waves pointed back to the same region where 3I Atlas was making its closest approach. Multiple spacecraft, separated by millions of kilometers and observing from different angles, were all seeing magnetic field disruptions that seemed to originate from the same source. This magnetic connection offered a potential explanation for at least part of the blue glow mystery. Magnetic fields play crucial roles in plasma physics, controlling how charged particles move and interact. If 3I Atlas was somehow interacting with the Sun's magnetic field, that interaction could accelerate electrons and ions to high energies. These energetic particles could then collide with neutral gas in the comet's coma, exciting atoms and molecules to emit light. The blue wavelengths might represent specific atomic transitions that occur when electrons strike carbon, oxygen, or nitrogen atoms with just the right energy. But this explanation raised new questions. Comets are fundamentally non-magnetic objects, composed of ice and rock that have no significant magnetic fields of their own. How could a non-magnetic body perturb the Sun's magnetic field strongly enough to create detectable disturbances millions of kilometers away? The interaction would require either an unexpectedly large conducting region around the comet, perhaps created by ionization of its extended coma, or some kind of direct mechanical force capable of pushing against magnetic field lines as 3I Atlas ploughed through the corona at tremendous speed. Scientists began developing a theoretical framework that could explain both the blue glow and the magnetic field perturbations through a single unified mechanism. The key insight came from considering what happens when an interstellar comet with an unusually massive coma encounters the extreme radiation environment close to the Sun. 3I Atlas had already demonstrated anomalous properties during its journey through the solar system, particularly its enormous estimated mass and the unusual carbon dioxide-rich chemistry detected by space telescopes. Perhaps these same exotic characteristics were now creating unprecedented behavior near perihelion. The hypothesis centered on ionization, the process by which atoms lose electrons when struck by high-energy radiation. Near Earth's orbit, solar ultraviolet light ionizes a small fraction of the gas in a typical comet's coma, perhaps 1% or less. But at the distance where 3I Atlas was passing, solar radiation arrived with more than 10 times the intensity. Every square meter of the comet's surface received ultraviolet photons at a rate that could strip electrons from atoms with brutal efficiency. If 3I Atlas was releasing gas at the prodigious rates suggested by its massive coma, this material would be instantly bathed in radiation, intense enough to ionize a substantial fraction of all atoms and molecules. An ionized coma would behave completely differently from the neutral gas clouds that surround typical comets. Instead of simply expanding into space and drifting away on the solar wind, ionized gas would respond to magnetic fields. The electrically charged particles would spiral along magnetic field lines, creating currents that could generate their own magnetic signatures. This conducting plasma envelope could easily reach dimensions of hundreds of thousands of kilometers, matching the observed size of the blue glow region. The interaction between this vast plasma cloud and the Sun's magnetic field would naturally create the perturbations that spacecraft magnetometers detected. The blue emissions could arise from several processes within this ionized environment. Electrons freed during ionization would be accelerated by electric fields that form naturally in plasma. These energetic electrons could collide with neutral atoms that hadn't yet been ionized, exciting them to emit light at characteristic wavelengths. The specific blue-green colors might represent emission from excited carbon dioxide ions, carbon monoxide molecules, and various metallic atoms released from dust grains, all glowing simultaneously in slightly different wavelengths that blended together to create the observed blue appearance. Computer simulations of this scenario showed promising results. When researchers modeled a massive comet releasing carbon dioxide-rich gas near the Sun, then calculated how solar radiation would ionize that gas and how the resulting plasma would interact with magnetic fields, the simulations produced glowing regions with sizes, brightnesses, and spectral properties roughly matching observations. The models weren't perfect. Several details didn't quite align, but they demonstrated that known physics could potentially explain the phenomenon without invoking exotic new processes or artificial mechanisms. High-resolution coronagraph images revealed a structure that transformed theoretical speculation into observable reality. As scientists processed multiple frames from both space-based and ground-based instruments, a distinctive pattern emerged in the blue glow itself. The emission wasn't uniform or spherical, as might be expected from simple fluorescence or thermal processes. Instead, it showed clear asymmetry with a sharp, curved boundary on the sunward side of 3I Atlas's position. This boundary looked remarkably similar to shock waves that form when supersonic aircraft push through Earth's atmosphere, or when the solar wind itself crashes into planetary magnetospheres. The curved structure, brightest along its leading edge and gradually fading behind, had the classic appearance of a bow shock. This phenomenon occurs when an object moves through a medium faster than disturbances can propagate through that medium. On Earth, we see bow shocks as sonic booms when jets exceed the speed of sound. In space, they form when the solar wind encounters planets, or when fast-moving plasma clouds plow through slower-moving material. What made this discovery remarkable was that 3I Atlas was creating a visible bow shock, not in the tenuous interplanetary medium, but in the relatively dense environment of the Sun's extended corona. The physics made sense once researchers ran the calculations. 3I Atlas was moving through its perihelion passage at speeds exceeding 100 kilometers per second, relative to the surrounding coronal plasma. The Sun's corona, despite being incredibly hot with temperatures of a few million degrees, is actually quite rarefied with densities far lower than the best laboratory vacuums achievable on Earth. But near the Sun, where 3I Atlas was passing, coronal densities increased substantially. The interstellar visitor was effectively ploughing through a medium that, while still extremely thin, by everyday standards, was dense enough to create resistance. As 3I Atlas moved, its extended coma of ionized gas pushed against the ambient coronal plasma. This collision created a shock front, a boundary where the relative velocity between the comet's material and the Sun's atmosphere dropped suddenly. On the upstream side of this boundary, approaching material traveled at the full orbital velocity. On the downstream side, the material had been slowed and compressed by the collision. The compression heated the plasma and changed its properties, potentially explaining some of the emission characteristics that made the blue glow so distinctive. The bow shock structure appeared most prominently in the blue wavelengths that had first caught astronomers' attention. Images taken in other wavelength ranges showed the structure less clearly or not at all, suggesting that whatever process created the blue emissions was intimately connected to the shock physics itself. Perhaps the shock compression heated plasma to temperatures optimal for producing the observed spectral lines, or maybe the shock accelerated electrons that then excited atoms and molecules to glow. The bow shock wasn't just an interesting visual feature, it was potentially the key to understanding the entire phenomenon. A breakthrough connection emerged when researchers compared the blue glow spectra with earlier observations of 3I Atlas taken months before perihelion. Back in August of 2025, the Very Large Telescope in Chile had detected something peculiar in the comet's coma: prominent emission lines from nickel atoms, while iron remained mysteriously absent. At the time, this chemical anomaly had puzzled scientists who expected these two metals to appear together, since they typically exist in similar proportions in cosmic materials. Now, as teams analyzed the blue glow phenomenon, they realized this earlier nickel detection might hold the key to understanding the perihelion emissions. Nickel atoms have a special property that makes them particularly effective at producing blue light under the right conditions. When nickel atoms absorb ultraviolet photons from the sun, electrons within the atoms jump to higher energy levels. These excited electrons don't stay in their elevated state for long. They quickly fall back down to lower energy levels, releasing the absorbed energy as new photons. The wavelengths of these emitted photons depend on the specific energy levels involved in the transition. And for nickel, several strong transitions produce light in the blue-green portion of the visible spectrum. Near perihelion, the ultraviolet radiation intensity from the sun increases dramatically. Each nickel atom in 3 I-Atlas's coma would be struck by UV photons at a rate thousands of times higher than at Earth's distance from the sun. This intense bombardment could drive the fluorescence process with exceptional efficiency. If 3 I-Atlas was releasing nickel atoms at substantial rates, either through direct sublimation from the nucleus or through destruction of nickel-bearing dust grains, the resulting fluorescence could potentially explain at least some of the observed blue glow. The energy budget calculations supported this hypothesis. Researchers estimated how much ultraviolet light was available at 3 I-Atlas's perihelion distance, and how efficiently nickel fluorescence could convert that UV energy into visible blue light. The numbers worked out favorably. If the comet's coma contained nickel at concentrations even moderately higher than typical solar system materials, and if that nickel was being liberated into atomic form rather than remaining locked in minerals or grains, the fluorescence process could produce blue emissions comparable to what observations actually showed. The 3 unidentified spectral lines that had puzzled scientists since the first ground-based observations gained new significance under this framework. Nickel has dozens of possible atomic transitions that can produce emission lines across the visible spectrum. Many of these transitions are weak and rarely observed in astronomical contexts because they require specific excitation conditions. Perhaps the extreme radiation environment near the sun was pumping nickel atoms into unusual excited states that produced emission lines not commonly seen in laboratory catalogues or previous astronomical observations. The mystery lines at 462, 478, and 493 nanometers might simply be rare nickel transitions that became visible only under the exceptional conditions of an interstellar comet passing close to the sun. The blue glow didn't surround 3 I-Atlas uniformly like a simple spherical halo. Detailed analysis of images from multiple spacecraft revealed a pronounced asymmetry that contained crucial clues about the underlying physical processes. The emission concentrated heavily on the hemisphere facing the sun, creating a teardrop-shaped envelope with its brightest region pointing directly toward our star. This lopsided distribution ruled out several potential explanations and pointed toward mechanisms that operated directionally rather than isotropically. If the blue glow resulted purely from thermal processes, heating the comet's surface and causing material to glow like hot metal, the emission pattern should have followed the temperature distribution across the nucleus. The sunward side would indeed be hottest and brightest, but the transition to the night side should have been gradual, following smooth curves dictated by heat conduction and radiation physics. Instead, the observed pattern showed a much sharper contrast, with the sunward emission dropping off more rapidly than simple thermal models predicted. Fluorescence mechanisms also struggle to fully explain the asymmetry. While solar ultraviolet radiation certainly arrived more intensely on the sunward hemisphere, that radiation could scatter and reflect within the coma, illuminating material on the night side as well. The gas and dust surrounding the nucleus weren't opaque barriers that completely blocked UV light. Photons could penetrate deep into the coma, exciting atoms and molecules throughout a large volume. Yet the blue glow showed remarkably little emission from the anti-solar hemisphere, as if some process was actively suppressing light production on the side facing away from the sun. The bow shock structure offered a more satisfying explanation for the observed asymmetry. Shock physics naturally creates sharp boundaries and directional effects. As 3 I Atlas ploughed through the coronal plasma, the shock front formed exclusively on the leading edge, the sunward side where the comet's motion compressed and heated the surrounding medium. Behind the shock, in the wake of the comet's passage, conditions would be completely different. The plasma there had already been disturbed and pushed aside, creating a cavity or tail region where densities, temperatures, and magnetic field configurations all differed dramatically from the upstream environment. The brightest blue emissions traced out the shock front itself, marking the boundary where fresh coronal plasma first encountered the comet's ionized coma. This collision zone represented the most energetic environment, where particles were being accelerated, compressed, and heated through shock processes. The emission intensity naturally peaked along this boundary and declined both upstream, where material hadn't yet been processed by the shock, and downstream, where material had already passed through the shock and was now cooling and expanding in the wake region. Time-lapse sequences constructed from multiple observations showed the asymmetric pattern maintaining its orientation relative to the Sun as 3 I Atlas moved along its trajectory. The brightest emission always pointed sunward, confirming that the phenomenon was driven by the direction of solar radiation and the comet's motion through the coronal plasma, not by any intrinsic asymmetry in the nucleus itself, or artifacts of viewing geometry from Earth's perspective. Radio telescopes around the world detected something unexpected during the blue glow event that added another layer to the mystery. Solar radio bursts are common phenomena, electromagnetic emissions at radio wavelengths that occur when energetic processes in the Sun's atmosphere accelerate electrons to high speeds. But the radio bursts detected on and around the second day of November 2025 showed timing and characteristics that correlated suspiciously well with 3 I Atlas's perihelion passage and the appearance of the blue optical emissions. The bursts fell into a category that solar physicists call type 3 radio emissions. These occur when beams of electrons traveling near the speed of light stream outward from the Sun along magnetic field lines. As these fast electrons interact with the surrounding plasma, they generate radio waves through a process called plasma emission. The frequency of the radio waves depends on the local plasma density, with higher frequencies coming from denser regions closer to the Sun and lower frequencies from more rarefied regions farther out. By tracking how the emission frequency changes over time, scientists can essentially watch electron beams racing away from the Sun. What made the November bursts unusual was their spatial origin and timing structure. Radio interferometry, which combines signals from multiple telescopes to create detailed images, revealed that several bursts appeared to originate from the same region of the corona where 3 I Atlas was passing. This wasn't unprecedented. Solar radio bursts can occur anywhere on the Sun. but the coincidence of location and timing suggested a possible connection between the interstellar visitor and the electron acceleration processes. The temporal correlation was even more striking. Several radio bursts occurred within minutes of visible brightening events in the blue glow, as if something was simultaneously producing both the optical emissions and the energetic electron beams. The time delays between the radio and optical signatures matched expectations for light travel time differences, and the slight lag expected as electron beams traveled from an acceleration region into lower density plasma where they could generate detectable radio emissions. If the correlation was real rather than coincidental, it implied that 3I Atlas's passage was triggering genuine particle acceleration events in the solar corona. The bow shock structure could potentially serve as an acceleration site, with the compression and turbulence at the shock front accelerating some electrons to relativistic speeds. These electrons would then escape along magnetic field lines, generating radio bursts as they streamed through the corona, while simultaneously contributing to the optical emissions by exciting atoms and molecules in 3I Atlas's coma through collisions. Alternative explanations remained possible. The Sun is an active environment where radio bursts occur frequently for reasons completely unrelated to passing comets. Perhaps the temporal correlation was merely chance, a statistical coincidence where normal solar activity happened to peak during the same time window when 3I Atlas reached perihelion. Distinguishing between genuine causation and random coincidence would require careful statistical analysis of the timing patterns and comparison with the Sun's baseline activity levels during the same period. Scientists searching through decades of astronomical archives found no precedent for what 3I Atlas was doing near the Sun. The historical record of comet observations stretched back centuries, with increasingly detailed data available from the space age onward. Hundreds of comets had been observed passing through perihelion at various distances, and dozens had approached much closer to the Sun than 3I Atlas. Yet none of them, not a single example in the entire catalogue of documented cometary behaviour, had produced emissions resembling the blue glow phenomenon. The sun grazers provided the most relevant comparison cases. These are comets that pass extremely close to the Sun, sometimes diving within a few solar radii of the visible surface. The most famous sun grazer family, named after the Great Comet of 1888, includes thousands of small comets discovered by space-based coronagraphs. Many of these objects completely disintegrate during their close approach, unable to survive the intense heating and tidal forces. Others emerge intact, but dramatically transformed by their encounter with the extreme solar environment. Comet Lovejoy in 2011 provided perhaps the best recent comparison. This sun grazer passed just 1.2 solar radii from the Sun's center, skimming through the lower corona itself in an encounter far more extreme than 3I Atlas's perihelion passage. Observations of Lovejoy showed spectacular comet activity, a brilliant tail of ionized gas glowing in ultraviolet wavelengths, clouds of dust vaporizing in the intense heat, and the comet nucleus itself surviving against all predictions. But Lovejoy's emissions followed expected patterns. The spectrum showed typical comet molecules like water, carbon monoxide, and hydroxyl radicals, all emitting at their characteristic wavelengths. No anomalous blue glow appeared. No unidentified spectral lines puzzled observers. Lovejoy behaved like a comet should behave, even under the most extreme conditions. The Kreutz sun grazers, hundreds of small comets observed by SOHO over nearly 3 decades, similarly showed no precedent for blue glow phenomena. These objects, many just tens or hundreds of meters across, passed through perihelion at distances where solar heating should have been far more intense than what 3I Atlas experienced. SOHO's instruments captured their final moments as they vaporized in the solar atmosphere, their dust and gas dispersing into the corona. The spectroscopic signatures from these dying comets revealed standard compositions: water ice mixed with dust, carbon-bearing molecules, and traces of metals. Nothing in the extensive SOHO catalogue matched the blue emissions or unusual chemistry associated with 3I Atlas. Even accounting for differences in comet size, composition, and exact perihelion distance, the absence of any historical analogue was troubling. If 3I Atlas's blue glow resulted from some combination of normal physical processes, those same processes should have operated, at least occasionally, in the thousands of previously observed comet-sun encounters. The fact that they apparently never had suggested that something about 3I Atlas itself was fundamentally different from every solar system comet ever studied. Laboratory scientists began investigating whether exotic dust grain compositions could explain the blue glow through a mechanism that normal solar system materials couldn't replicate. The idea centered on a fundamental difference between interstellar and solar system dust. Every grain of dust in our solar system formed from the same primordial cloud that created the Sun and planets 4.6 billion years ago. This material had been processed through various cycles of heating, melting, and chemical alteration, but it all shared a common origin and broadly similar elemental abundances. Interstellar dust told a different story. Material drifting through the space between stars represented contributions from countless stellar systems, each with its own unique formation history and chemical composition. Some grains originated from supernovae that synthesized heavy elements through nuclear fusion. Others came from cool giant stars that ejected carbon-rich or oxygen-rich materials depending on their internal chemistry. Still others formed in the outflows from young stellar systems with elemental abundances quite different from our Sun's composition. 3I Atlas carried dust forged in an alien stellar environment, possibly billions of years ago. The earlier detection of prominent nickel emissions without corresponding iron already hinted that this dust had unusual composition. If the refractory elements, those that remain solid even at high temperatures, existed in ratios significantly different from solar system materials, the dust grains could have optical properties that nobody had characterized before. Researchers proposed that these exotic grains might be exceptionally efficient at absorbing solar ultraviolet radiation and re-emitting that energy at visible blue wavelengths. Certain mineral compositions show strong absorption features in the UV, combined with fluorescence emission in the blue-green region. If 3I Atlas's dust happened to be dominated by such materials, the intense UV bombardment near perihelion could drive fluorescence with far greater efficiency than typical silicate or carbon grains found in solar system comets. The grain destruction process added another layer of complexity. Near the Sun, dust grains experience heating that can reach temperatures of thousands of degrees within seconds. This extreme heating doesn't affect all grain types equally. Grains with lower vaporization temperatures would disintegrate first, releasing their constituent atoms into the gas phase. If 3I Atlas carried grains that vaporized more readily than typical comet dust, perhaps due to different chemical bonding or crystal structures, this could liberate unusual amounts of metallic atoms, like nickel, into the coma, where they could contribute to the blue emissions. Laboratory experiments were already underway to test these ideas. Scientists created synthetic dust grains with various exotic compositions, then subjected them to intense UV radiation, matching solar conditions at different distances. They measured the resulting emission spectra to see if any combination of elements and minerals could reproduce the observed blue glow characteristics. Early results showed promise. Certain nickel-rich silicate compositions produced enhanced blue emissions, though none yet matched observations perfectly. The challenge was that parameter space remained vast, countless possible grain compositions and structures that nobody had yet tested. The unusually high carbon dioxide abundance detected in 3I Atlas months before perihelion took on new significance as scientists tried to explain the blue glow. Back in August of 2025, observations by the James Webb Space Telescope had revealed that carbon dioxide dominated the comet's volatile emissions to a degree rarely seen in solar system comets. The ratio of carbon dioxide to water vapor ranked among the highest ever measured, suggesting that 3I Atlas formed in exceptionally cold conditions, far from its parent star where carbon dioxide could freeze as readily as water ice. Carbon dioxide molecules behave differently from water when exposed to intense solar radiation. When ultraviolet photons strike a carbon dioxide molecule with sufficient energy, they can break it apart through a process called photodissociation. The molecule fragments into carbon monoxide and oxygen, or sometimes into individual carbon and oxygen atoms. These fragmentation products are themselves reactive. They can recombine in various ways or interact with other molecules to create a complex cocktail of chemical species. But photodissociation isn't the only fate awaiting carbon dioxide near the sun. Intense UV radiation can also ionize the molecules, stripping away electrons to create positively charged carbon dioxide ions. These ions have electronic structures quite different from neutral carbon dioxide, and they emit light at different wavelengths when their electrons transition between energy levels. Several of the emission lines that carbon dioxide ions produce fall squarely in the blue portion of the visible spectrum. Calculations showed that near perihelion, where solar UV intensity exceeded 10 times the level at Earth's orbit, a substantial fraction of 3I Atlas's carbon dioxide would be ionized within seconds of sublimating from the nucleus. If the comet was releasing carbon dioxide at the prodigious rates suggested by earlier observations, this could create an enormous envelope of glowing carbon dioxide ions, extending hundreds of thousands of kilometers from the nucleus. The blue emissions from these ions could potentially account for a significant portion of the observed glow. The carbon monoxide produced by carbon dioxide photodissociation added another layer to this chemistry. Carbon monoxide molecules also absorb UV radiation and can be excited to emit light at various wavelengths. Some carbon monoxide transitions produce blue-green emissions that could blend with the carbon dioxide ion emissions to create the complex spectral signature that observers were measuring. The unusual chemistry might also explain why 3I Atlas behaved so differently from solar system comets that had passed even closer to the sun. Most comets show water-dominated compositions, with carbon dioxide present, but usually as a minor component compared to water. The sun grazers that survived close perihelion passages were fundamentally water ice objects that happened to contain some frozen carbon dioxide. 3. I-Atlas represented something different, a carbon dioxide-dominated object where water played a secondary role. This inverted composition meant that the dominant chemistry near perihelion involved carbon dioxide processes rather than the water-driven chemistry that characterized typical comets. The blue glow might simply be what happens when you heat a carbon dioxide comet to extreme temperatures in a way that had never been observed before. A significant portion of the scientific community pushed back against suggestions that the blue glow represented anything beyond well understood but rarely observed plasma physics. These researchers emphasized that the universe operates through natural laws that have been tested and validated across countless observations. Unusual didn't mean inexplicable, and certainly didn't justify invoking exotic mechanisms when conventional physics might suffice. The aurora comparison provided one of their strongest arguments. Earth's auroras produce spectacular colored lights, including brilliant blues and greens, through processes involving charged particles colliding with atmospheric gases. When electrons accelerated by Earth's magnetic field strike oxygen and nitrogen molecules in the upper atmosphere, those molecules emit light at characteristic wavelengths that create the dancing curtains visible from high latitudes. The physics is well understood. Particle acceleration followed by collisional excitation and radiative emission. 3. I-Atlas's blue glow could result from, essentially, the same process operating in a different environment. Instead of Earth's magnetic field accelerating electrons into our atmosphere, the Sun's magnetic field and the bow shock around the comet could be accelerating electrons that then collided with gas in the comet's coma. The blue wavelengths would naturally emerge from excitation of carbon, oxygen, and nitrogen, the same elements that produce blue auroral emissions on Earth. Scale this process up to operate over regions hundreds of thousands of kilometers across with a more intense radiation field, and you'd expect a bright blue glow exactly like observations showed. Jupiter's magnetosphere offered another terrestrial analogue. The giant planet sports powerful auroras at both poles, driven by its enormous magnetic field and fed by volcanic gases from its moon Io. These Jovian auroras include blue emissions from ionized hydrogen and other species, demonstrating that planetary-scale plasma processes readily produce blue light through completely natural mechanisms. The physics governing Jupiter's auroras, Earth's auroras, and potentially 3 I-Atlas's blue glow all followed the same fundamental principles of plasma behavior and atomic physics. Conservative scientists pointed out that every supposedly anomalous aspect of 3 I-Atlas had potential natural explanations. The massive size estimate might be incorrect, based on preliminary data that would be revised as analysis improved. The nickel without iron chemistry could result from selective release mechanisms that preferentially liberated nickel from certain mineral phases, while iron remained bound in more refractory compounds. The carbon dioxide-rich composition, while unusual, wasn't unprecedented, and certainly didn't violate any physical laws. The bow shock structure itself demonstrated that conventional physics could explain at least the morphology of the blue glow. Shock waves form naturally whenever objects move through plasma faster than information can propagate through that medium. The asymmetric emission pattern followed directly from shock geometry. The magnetic field perturbations resulted from currents flowing in the ionized coma, exactly as plasma physics textbooks predicted. Each puzzle piece, when examined carefully, fit within the framework of established science without requiring revolutionary new physics or artificial explanations. The burden of proof rested on those claiming something extraordinary, and that proof remained elusive in the face of plausible natural mechanisms. Astrochemists offered a different perspective that didn't require invoking artificial mechanisms, but still emphasized how fundamentally alien 3I Atlas might be. These scientists specialized in understanding chemical processes under extreme conditions, from the frigid molecular clouds where stars are born to the superheated plasma surrounding neutron stars. Their expertise suggested that molecules formed in different stellar environments could behave in ways that solar system chemistry had never prepared us to expect. The formation environment mattered enormously for determining what chemical compounds could exist in a comet's nucleus. 3I Atlas had been wandering through interstellar space for potentially millions or billions of years after being ejected from a stellar system with its own unique characteristics. That parent system might have had a different ratio of heavy elements compared to our Sun, leading to ice compositions quite unlike anything found in the solar system. The carbon dioxide dominance already hinted at formation conditions beyond what our own Kuiper belt or Oort cloud could produce. But exotic ice compositions represented just the beginning of potential chemical surprises. Interstellar chemistry operates through pathways that don't occur in planetary systems. Cosmic rays, high-energy particles streaming through the galaxy, bombard interstellar material continuously. This radiation can drive chemical reactions that create unusual molecules not found in more sheltered environments. Organic compounds of staggering complexity have been detected in interstellar clouds through radio astronomy. If 3I Atlas carried such materials frozen into its nucleus, heating them near the Sun could trigger decomposition reactions that released gases with no solar system analog. The unidentified spectral lines gained new interpretations under this framework. Perhaps those three mysterious emission features at 462, 478, and 493 nanometers didn't come from rare nickel transitions at all. They might represent emissions from molecular species that had never been synthesized in terrestrial laboratories or detected in previous astronomical observations. Organic molecules with unusual structures, molecular ions with excited electronic states, or even transient radical species that existed only briefly during the decomposition process could all produce emission lines at wavelengths not catalogued in standard databases. Laboratory astrochemists began designing experiments to test these possibilities. They created ice mixtures with compositions matching 3I Atlas's inferred chemistry, then subjected these samples to radiation fields and heating profiles that mimicked conditions near the Sun. The goal was to identify what gases would be released and what spectral signatures those gases would produce when excited by UV radiation. Early experiments revealed surprising complexity. Carbon dioxide-rich ices containing traces of organic materials produced emission spectra that differed substantially from pure carbon dioxide or pure water ice samples. The exotic chemistry hypothesis had the advantage of explaining multiple anomalies simultaneously. Unusual dust compositions could account for enhanced nickel emissions and efficient blue fluorescence. Novel molecular species could explain the unidentified spectral lines. The overall strangeness of 3I Atlas, from its massive size to its peculiar chemistry to its unprecedented blue glow, all fit naturally if this visitor truly represented materials processed through chemical pathways that operated nowhere in our solar system. The blue glow phenomenon gave renewed energy to technological interpretations of 3I Atlas that had circulated since the object's discovery months earlier. Proponents of artificial origin hypotheses pointed out that the timing of the blue emissions, appearing precisely at perihelion, when the object was hidden behind the Sun from Earth's perspective, fit uncomfortably well with predictions about how a probe might behave when stressed by extreme conditions. The emissions could represent electromagnetic signatures from systems operating under duress, struggling to maintain function in the intense radiation environment. The energy requirements for the blue glow added fuel to these arguments. Calculations showed that sustaining the observed brightness required continuous power input comparable to a significant solar flare. For a natural object, this energy had to come from solar radiation through various indirect mechanisms like fluorescence or plasma heating. But those mechanisms involved inherent inefficiencies, meaning the comet needed to capture and process enormous amounts of solar energy to produce the visible output. A technological system with even modest efficiency could potentially generate the same optical output with far less total energy expenditure. The spectral signatures took on different meanings under this interpretation. The 3 unidentified emission lines might not represent exotic chemistry or rare atomic transitions at all. They could be electromagnetic emissions from electronic systems, perhaps waste heat from power generation being radiated at specific wavelengths, determined by material properties of artificial components. The blue color itself might be deliberate, an optical signature designed for identification or communication rather than an accidental byproduct of natural processes. The bow shock structure gained ambiguous significance. While shock waves certainly form naturally around objects moving through plasma, the precise geometry and brightness distribution of 3I Atlas's bow shock showed features that some researchers found suggestive of controlled processes. The asymmetry was perhaps too perfect, too stable over time, compared to the turbulent and variable shock structures typically observed around natural bodies. If the object was using some form of propulsion or field generation, those systems could be shaping the surrounding plasma in ways that mimicked natural shock formation, but with subtle differences. Critics immediately pushed back against these technological interpretations with the same arguments they'd raised before. Extraordinary claims required extraordinary evidence, and the blue glow, while unusual, didn't constitute definitive proof of artificial origins. Every observed characteristic had at least plausible natural explanations, even if those explanations required invoking rare conditions or poorly understood physics. The absence of clearly artificial signatures like narrowband radio transmissions, geometric structures resolved in images, or trajectory modifications beyond what outgassing could explain, meant the technological hypothesis remained speculation rather than established fact. The debate highlighted fundamental questions about how science should approach genuinely anomalous observations. At what point did accumulating circumstantial evidence justify seriously considering unconventional explanations. How many coincidences and unexplained features needed to pile up before artificial origin moved from fringe speculation to legitimate scientific hypothesis? The blue glow added one more item to the list of 3 I-Atlas anomalies, but whether that list had crossed some threshold of significance remained contentiously debated. Solar physicists proposed a mechanism that could explain both the blue glow and the radio bursts through a single dramatic process called magnetic reconnection. This phenomenon occurs when magnetic field lines with opposite orientations are forced together, suddenly snap and reconfigure into a lower energy state. The energy released during this reconfiguration gets converted into heat and kinetic energy, accelerating particles to tremendous speeds and heating plasma to millions of degrees. Magnetic reconnection drives some of the Sun's most violent events, including solar flares and coronal mass ejections that can disrupt satellites and power grids on Earth. The scenario required specific geometric conditions that 3 I-Atlas's passage might have created. As the interstellar visitor ploughed through the corona with its ionized coma interacting with the Sun's magnetic field, it could have pushed field lines together in ways that forced reconnection events to occur. The comet essentially acted as a blunt object dragging through a magnetically structured medium, compressing and distorting field lines until they reached breaking points where reconnection became inevitable. When magnetic reconnection occurs, it releases energy in multiple forms simultaneously. Some energy goes into heating the local plasma to extreme temperatures, potentially creating regions hot enough to emit X-rays and extreme ultraviolet radiation. Other energy accelerates electrons and ions to relativistic speeds, creating beams of particles that stream away along newly reconfigured magnetic field lines. These particle beams could generate both the type Third radio bursts detected by ground-based telescopes and contribute to exciting atoms in 3 I-Atlas's coma to produce blue optical emissions. The reconnection scenario elegantly explained several puzzling correlations. The temporal coincidence between radio bursts and optical brightening events would result naturally from reconnection releasing energy in both electromagnetic and particle forms nearly simultaneously. The asymmetric distribution of the blue glow would reflect the geometry of magnetic field lines in the corona, which naturally concentrate near the Sun's equatorial regions and show complex structure shaped by the solar wind and coronal heating processes. Computer simulations of magnetic reconnection in the specific environment of a comet passing through the corona showed promising results. When researchers modeled the magnetic field topology expected near 3 and I-Atlas and calculated where reconnection events would most likely occur, the resulting patterns matched observed features of the blue glow reasonably well. The models predicted bright emission regions on the sunward hemisphere, where field line compression would be strongest, gradual dimming toward the night side, and occasional bursts of enhanced brightness corresponding to individual reconnection events. However, the reconnection hypothesis faced challenges explaining the sustained nature of the blue glow. Magnetic reconnection typically produces transient bursts of energy lasting seconds to hours, not the continuous emission observed over multiple days. The models required ongoing reconnection events occurring repeatedly as 3 I-Atlas moved through the corona, essentially assuming that the comet continuously triggered new reconnection sites as it progressed along its trajectory. Whether this scenario was physically plausible remained an active area of theoretical investigation and debate among solar physicists. A troubling inconsistency emerged when scientists calculated how much mass 3I Atlas should have lost during its perihelion passage. The extreme heating near the Sun should have vaporized enormous quantities of ice and dust from the nucleus surface. Standard comet physics, validated through decades of observations, provided clear predictions about ablation rates under various temperature and radiation conditions. When researchers applied these models to 3I Atlas's perihelion environment, the numbers painted a disturbing picture. At the closest approach distance, solar radiation would heat the nucleus surface to temperatures exceeding 1000 degrees Celsius. Ice doesn't just sublimate gently. At these temperatures, it explosively converts to vapor at rates measured in centimeters per hour of surface recession. For an object with the 5-kilometer diameter attributed to 3I Atlas, the total mass loss during just the few hours near perihelion should have reached billions of kilograms. Dust grains embedded in the ice would be released as the ice holding them together vaporized, adding to the mass loss through mechanical erosion and radiative blow-off. The energy budget made the problem even more severe. Solar radiation delivers roughly 10 megawatts per square meter at the distance where 3I Atlas passed. A 5-kilometer diameter nucleus presents a cross-sectional area of about 20 square kilometers to the Sun, intercepting over 200 gigawatts of radiant power. Even accounting for reflection and re-radiation, the amount of energy available for driving ablation was staggering. This energy had to go somewhere, either heating the interior, driving sublimation, or vaporizing surface materials. Yet preliminary observations of 3I Atlas after perihelion suggested the object emerged relatively intact. The brightness and size of the coma didn't show the dramatic increase expected if the nucleus had lost a substantial fraction of its mass. The orbital elements remained consistent with the pre-perihelion trajectory, showing no evidence of significant mass loss that would have altered the object's response to solar radiation pressure. It was as if 3I Atlas had somehow shrugged off the extreme heating that should have devastated its surface. Several potential explanations struggled to resolve this discrepancy. Perhaps the nucleus wasn't actually 5 kilometers across, but much smaller, reducing the total surface area exposed to heating and making the expected mass loss more modest. But this would contradict the mass estimates derived from the anomalously weak non-gravitational acceleration. A smaller nucleus couldn't easily explain both the minimal rocket effect and the survival of perihelion passage. Alternatively, the nucleus might have unusual thermal properties that protected it from ablation. A surface layer of refractory materials with high melting points could act as insulation, preventing heat from penetrating to the ice-rich interior. Some asteroids show this kind of protective crust formed through space weathering over millions of years. If 3I Atlas had developed an exceptionally effective insulating layer during its interstellar journey, that could explain the apparently minimal mass loss despite extreme heating. The blue glow itself might represent part of the answer. If the emissions resulted from processes that efficiently radiated away absorbed solar energy, this could reduce the amount of heat available for driving ablation. International teams coordinated an unprecedented multi-wavelength observation campaign to capture the blue glow across the entire electromagnetic spectrum. Visible light observations had revealed the phenomenon's existence, but the full story required data from radio wavelengths stretching meters in length, all the way through optical and ultraviolet bands, to X-rays with wavelengths measured in billionths of a meter. Each wavelength range probed different physical processes and provided unique insights into what was happening around 3 I Atlas. Radio observations at frequencies from a few megahertz to several gigahertz tracked plasma density and temperature in the extended envelope surrounding the comet. The radio emission intensity and spectral characteristics revealed how ionized gas was distributed throughout the coma, and how that plasma interacted with the solar wind. Ground-based interferometers, combining signals from multiple telescopes, created radio images with resolution fine enough to map structure within the glowing region, revealing turbulent patterns and potential shock boundaries. Infrared observations from space-based telescopes measured thermal emission from dust grains and provided estimates of their temperature and size distribution. The Spitzer Space Telescope archives and data from ground-based infrared facilities showed how dust temperature varied across the coma, creating maps of heating patterns that reflected where solar radiation was being absorbed most efficiently. These thermal maps didn't perfectly align with the visible blue glow, suggesting that the optical emissions and dust heating involved at least partially distinct physical processes. Ultraviolet observations proved particularly revealing because many atomic and molecular transitions produce their strongest emissions in UV wavelengths. Space telescopes operating in the far and extreme ultraviolet detected emission lines from highly ionized atoms, including carbon, oxygen, and nitrogen, stripped of multiple electrons. The intensity ratios of these emission lines provided diagnostics of plasma temperature and density that complemented information from other wavelength ranges. The UV spectrum showed that 3 I Atlas's immediate environment contained plasma heated to temperatures exceeding 100,000 degrees, far hotter than the few thousand-degree temperatures typical of neutral comet comas. X-ray observations represented the high-energy frontier of the multi-wavelength campaign. X-ray telescopes detected faint but definite emission from the region around 3 I Atlas, indicating that extremely hot plasma or highly energetic particle interactions were occurring. The X-ray spectrum showed characteristic features of thermal emission from million-degree plasma, confirming that at least some portions of the environment had been heated to temperatures comparable to the Sun's corona itself. When researchers compiled all these observations into a comprehensive picture, patterns emerged that single wavelength studies would have missed. The blue optical glow represented just one component of a complex multi-temperature, multi-density structure. Cool neutral gas coexisted with warm, partially ionized material and hot, fully ionized plasma, all occupying different spatial regions and contributing to emissions at different wavelengths. The bow shock showed up most prominently in visible light and UV, but left signatures across the entire spectrum. This multi-wavelength view transformed the blue glow from a simple optical curiosity into a window on extraordinarily complex physics, operating across many energy scales simultaneously. Observatories around the world deployed their coronagraphs in a coordinated effort to track the blue glow's evolution as 3 I Atlas moved through its closest approach to the Sun. These specialized instruments, designed to block out the overwhelming brightness of the solar disk to reveal the faint corona, represented humanity's eyes on a phenomenon occurring in one of the most challenging observation environments imaginable. From Hawaii to Chile, from the American Southwest to European mountain peaks. Telescopes turned toward the Sun with filters and detectors, optimized to capture every possible detail. The time series data they collected revealed that the blue glow wasn't static. Its brightness varied over timescales of hours, showing fluctuations that suggested dynamic rather than steady-state processes. Some brightness changes appeared random, perhaps reflecting turbulence in the plasma or variations in solar wind conditions. Other variations showed periodic patterns, repeating every few hours in ways that might correlate with rotation of 3I Atlas's nucleus, or with orbital dynamics as the comet's viewing geometry changed relative to Earth-based observers. Mauna Kea Observatory in Hawaii provided crucial coverage during periods when the comet's position in the sky favored observations from Pacific longitudes. The high-altitude site, perched above 40% of Earth's atmosphere, offered exceptionally clear viewing conditions. Instruments there captured detailed spectra, showing how individual emission lines brightened and faded independently, indicating that different physical processes were turning on and off at different times. The nickel emission lines showed particularly strong variability, sometimes dominating the spectrum, and other times fading to barely detectable levels. Cerro Tololo in Chile complemented the Hawaiian observations by covering periods when Earth's rotation carried the comet below the horizon for Northern Hemisphere sites. This southern perspective also provided slightly different viewing geometry, allowing astronomers to construct three-dimensional models of the blue glow structure by comparing how it appeared from different vantage points. The models revealed that the emission extended not just outward from the nucleus, but also along the comet's orbital path, creating an elongated envelope that traced the trajectory through space. The coordinated network approach proved essential for capturing transient, brightening events that lasted only minutes to hours. Multiple observatories recorded sudden increases in blue emission intensity that appeared and faded within their observation windows. Without continuous coverage from multiple sites, these events would have been missed entirely or dismissed as instrumental artifacts. The confirmation from independent facilities established that the brightenings were real phenomena, possibly corresponding to individual reconnection events or sudden releases of material from the nucleus. Data sharing protocols allowed teams to compare their observations in near real time, adjusting observation strategies on the fly to capture unexpected developments. When one observatory detected an unusual spectral feature, others could immediately point their instruments to confirm and characterize it. This dynamic response capability transformed the observation campaign from a passive monitoring effort into an active investigation that adapted to the phenomenon as it unfolded, maximizing the scientific return from humanity's collective astronomical infrastructure. Solar Orbiter provided a perspective on the blue glow that no ground-based telescope could match. The European Space Agency spacecraft, launched in 2020 to study the Sun from unprecedented angles, happened to be positioned at a fortunate location during 3I Atlas's perihelion passage. While Earth-based observers and Parker Solar Probe viewed the phenomenon from certain angles, Solar Orbiter watched from a completely different vantage point, roughly 90 degrees away along its own orbit around the Sun. This geometric separation allowed scientists to construct true three-dimensional views of the blue glow structure. The spacecraft's instruments revealed that the emission extended far beyond what initial estimates had suggested. From Earth's perspective, the blue glow appeared as a relatively compact structure, perhaps 100,000 kilometers across. But solar orbiters' side-on view showed that the emission stretched along 3 I-Atlas's orbital path for distances exceeding 500,000 kilometers. The comet was leaving a glowing trail through the corona, a luminous wake that persisted for hours after the nucleus itself had passed. This extended structure suggested that the blue glow didn't originate solely from material immediately surrounding the nucleus. Instead, gas and plasma released from 3 I-Atlas continued glowing long after being ejected, marking the comet's trajectory through space like a cosmic contrail. The physics driving this extended emission remained uncertain. Perhaps the material stayed ionized and excited for extended periods due to the intense radiation environment. Or maybe the bow shock and magnetic field interactions created conditions that maintained the glow far downstream from the nucleus. Solar Orbiter's ultraviolet imager captured details invisible to visible light instruments. The UV images showed multiple, distinct emission regions within the blue glow structure, each with different spectral characteristics suggesting different physical conditions. One region showed strong emission from highly ionized carbon and oxygen, indicating temperatures exceeding 100,000 degrees. Another showed cooler molecular emissions, with temperatures below 10,000 degrees. These regions appeared spatially separated, creating a layered structure like an onion with different temperature zones at different distances from the nucleus. The 3-dimensional perspective also resolved a puzzle about the bow shock structure. From Earth's viewpoint, the shock appeared as a simple curved boundary on the sunward side of the nucleus. Solar Orbiter's perpendicular view revealed that the shock actually formed a complex 3-dimensional surface, more like a bullet shape than a simple hemisphere. The shock extended backward along the orbital path, creating a boundary that separated undisturbed coronal plasma from material that had been processed by the comet's passage. Time-stamped observations from Solar Orbiter, Parker Solar Probe, and ground-based facilities allowed scientists to track changes in the blue glow simultaneously from multiple directions. When a brightening event occurred, all 3 observation perspectives recorded it within seconds, confirming that the variations were real physical changes rather than viewing geometry effects. The multi-angle coverage transformed the blue glow from a 2-dimensional image into a fully realized 3-dimensional phenomenon that scientists could analyze using geometric and physical models. Scientists around the world threw themselves into the challenge of identifying every emission line visible in the blue glow spectrum. This task, seemingly straightforward, turned into one of the most frustrating aspects of the entire investigation. Spectroscopic databases contain millions of measured atomic and molecular transitions accumulated over more than a century of laboratory work and astronomical observations. Yet matching the observed lines to catalogue entries proved far more difficult than anyone anticipated. The strong emission features at common wavelengths presented no mystery. Lines from ionized carbon at 514 nanometers, neutral oxygen at 557 and 630 nanometers, and various nitrogen transitions all appeared exactly where expected, with intensities that made sense given the probable composition of 3 I-Atlas's coma. These familiar signatures confirmed that carbon, oxygen, and nitrogen, the building blocks of most cometary volatiles, were present and behaving more or less as predicted. but dozens of weaker lines scattered throughout the blue-green region of the spectrum defied identification. Teams cross-reference these mystery lines against every database they could access. The NIST Atomic Spectra database, containing hundreds of thousands of measured transitions. The HITRAN Molecular Spectroscopy Catalogue, with millions of entries for molecules, ranging from simple diatomics to complex organics. Specialized databases for ionized species, forbidden transitions, and exotic excited states. Nothing matched perfectly. The three strongest unidentified lines at 462, 478, and 493 nanometers became the focus of intensive investigation. Laboratory spectroscopists attempted to reproduce these emissions by creating plasmas with various compositions and exciting them with UV radiation matching solar conditions. They synthesized unusual molecular species predicted by astrochemical models and measured their emission spectra. They calculated theoretical wavelengths for rare atomic transitions that might occur only under extreme conditions. Despite these efforts, no laboratory experiment or calculation definitively explained all three mystery lines simultaneously. One possibility was that the lines represented blends, multiple weak transitions from different species that happened to fall at nearly the same wavelength and appeared as single features when viewed through instruments with limited spectral resolution. Ground-based spectrographs typically achieved resolving powers of a few thousand, meaning they could distinguish wavelengths separated by about 1/10 of a nanometer. If several transitions clustered more tightly than that, they would blur together into an apparently single line that wouldn't match any individual transition in the databases. The extreme physical conditions near perihelion opened another possibility. At temperatures exceeding 100,000 degrees and under intense UV bombardment, atoms and molecules could be excited into energy states rarely achieved in laboratory experiments. These exotic excited states might decay through pathways that produced emission at wavelengths not previously catalogued because they simply never occurred in terrestrial conditions or in other astronomical environments where spectroscopy had been performed. 3. iAtlas might be creating a plasma laboratory with parameter combinations that had never been studied before. Polarimetric observations added a crucial new dimension to understanding the blue glow by revealing how light waves were oriented as they traveled from 3 iAtlas toward Earth. Light consists of electromagnetic waves oscillating perpendicular to their direction of travel, and these oscillations can be oriented randomly or preferentially aligned in particular directions. When light becomes polarized, it carries information about the physical processes that produced it, or the materials it passed through on its journey. Specialized polarimeters attached to several telescopes measured the degree and direction of polarization across the blue glow. The results showed that roughly 30% of the blue light was polarized, a significant fraction that immediately ruled out certain emission mechanisms. Direct thermal emission from hot gas produces unpolarized light because the random thermal motions of atoms create waves oscillating in all directions equally. The fact that 3 iAtlas's blue glow showed substantial polarization meant that scattering processes must be involved, where photons changed direction after interacting with particles. 2 types of scattering could explain the polarization signature. Rayleigh scattering occurs when light interacts with particles much smaller than its wavelength. like air molecules scattering sunlight to create Earth's blue sky. This process naturally produces polarized light, with the degree of polarization depending on the scattering angle between the incoming and outgoing photon directions. My scattering involves larger particles, comparable in size to the light's wavelength, such as dust grains. This also produces polarization, though with different angular dependencies than Rayleigh scattering. The measured polarization pattern across the blue glow provided clues about particle sizes and distributions. Regions showing higher polarization percentages likely contained smaller particles or electrons that scattered light through Rayleigh-like processes. Areas with lower polarization might contain larger dust grains, where my scattering dominated, or they might represent a mixture of scattered and directly emitted light that diluted the polarization signal. By mapping polarization across the entire structure, scientists could infer how dust and free electrons were distributed throughout the coma. The polarization direction, the angle at which the light waves oscillated, revealed additional information. For scattering processes, polarization direction relates geometrically to the locations of the light source, scattering particles, and observer. The blue glow showed polarization oriented roughly perpendicular to the direction toward the sun, exactly as expected if sunlight was being scattered by particles in 3 I-Atlas's coma. This confirmed that at least some of the blue emission resulted from solar photons being redirected toward Earth, rather than from atoms spontaneously emitting light after excitation. However, the polarization wasn't uniform across all wavelengths. When scientists measured polarization separately for different colors within the blue-green region, they found variations. Some wavelengths showed stronger polarization than others, suggesting that multiple emission and scattering processes operated simultaneously. Direct fluorescence from excited atoms contributed unpolarized emission at specific wavelengths, while scattered sunlight added polarized emission across a broad range of wavelengths. Disentangling these contributions required sophisticated modeling that matched both the spectral and polarization signatures simultaneously. The blue glow event transformed from a curiosity about an interstellar visitor into a breakthrough opportunity for solar physics. For decades, scientists had struggled to understand fundamental processes occurring in the sun's corona, that million-degree atmosphere extending millions of kilometers from the solar surface. The corona's extreme temperature, far hotter than the sun's visible surface beneath it, represented one of astronomy's most persistent puzzles. How does energy travel outward from the cooler surface to heat the corona to such extraordinary temperatures? 3. I-Atlas's passage provided an unexpected natural experiment that illuminated these processes in unprecedented ways. The bow-shock formation offered direct evidence of how plasma behaves under conditions that couldn't be replicated in laboratory experiments. Earth-based plasma physics experiments operate at scales of meters with durations of milliseconds. The bow-shock around 3 I-Atlas spanned hundreds of thousands of kilometers and persisted for days, providing observations of shock dynamics at scales and timescales impossible to achieve artificially. Scientists used these observations to test theoretical models of shock formation, particle acceleration, and energy dissipation that applied not just to comets, but to understanding the solar wind's interaction with planets and interstellar space. The magnetic field perturbations detected by multiple spacecraft provided rare data about how objects can influence the Sun's extended magnetic environment. Normally, scientists observe the corona's magnetic field indirectly through its effects on plasma flows and emissions. 3I Atlas essentially served as a probe that poked the magnetic field and allowed researchers to watch how it responded. The field line distortions, wave propagation, and potential reconnection events all contributed data points that constrained models of coronal magnetic field topology and dynamics. The particle acceleration signatures, particularly the Type 3 radio bursts, correlated with blue glow brightening events, offered insights into how the corona accelerates electrons to high energies. This acceleration process operates throughout the solar system, from the corona itself to the radiation belts around planets to astrophysical jets in distant galaxies. Understanding the mechanisms through direct observation of 3I Atlas's environment helped refine theories that applied across multiple contexts in space physics and astrophysics. The extended observation campaign demonstrated the power of multi-wavelength, multi-platform coordination for studying transient solar phenomena. Space weather events like coronal mass ejections and solar flares occur unpredictably, making comprehensive observations challenging. 3I Atlas's perihelion passage was predictable months in advance, allowing unprecedented coordination between ground-based observatories, near-Earth spacecraft, and solar system explorers like Parker Solar Probe and Solar Orbiter. The data collection strategies and analysis techniques developed during this campaign established templates for future studies of solar transients. Perhaps most importantly, the blue glow event revealed that the corona could respond to intruders in ways that standard models hadn't fully predicted. The sustained brightness, complex spectral signatures, and dynamic variations all indicated that corona-comet interactions involved physics more complicated than simple heating and ionization. Future models of how material interacts with the solar atmosphere would need to incorporate lessons learned from 3I Atlas, improving predictions for everything from space weather forecasting to understanding how stellar winds interact with exoplanetary atmospheres around distant stars. The interstellar visitor had inadvertently advanced solar physics in ways that would benefit research for years to come. The blue glow phenomenon offered unprecedented insights into what happens when materials from interstellar space collide with stellar environments. For billions of years, matter has flowed between stars throughout the galaxy, carrying chemical signatures and physical properties from one stellar system to another. 3I Atlas represented a messenger from this vast interstellar ocean, and its behavior near the Sun revealed how interstellar and stellar materials interact when they meet. The chemistry alone told a remarkable story about conditions in the space between stars. Carbon dioxide dominated 3I Atlas's volatile composition to a degree rarely seen in solar system objects, reflecting formation conditions in the frigid outer reaches of some distant planetary system, where temperatures dropped below -125 degrees Celsius. This exotic ice composition survived intact through potentially millions of years of interstellar travel, preserved in the deep freeze of space far from any warming star. When this alien ice finally encountered intense solar radiation during perihelion passage, it responded in ways that revealed both universal physical principles and unique characteristics of interstellar materials. The dust grains carried by 3I Atlas similarly represented samples of interstellar material that formed in a different stellar environment. The prominent nickel emissions without corresponding iron suggested mineral compositions or grain structures quite different from solar system dust. These grains had been exposed to cosmic ray bombardment, interstellar shocks, and radiation from distant stars during their journey through space. The processing they underwent between stellar systems modified their physical and chemical properties in ways that became apparent only when they were suddenly heated to extreme temperatures near the Sun. Understanding how interstellar material behaves in stellar environments has implications far beyond cometary science. Throughout the galaxy, stars move through interstellar clouds. Planetary systems interact with streams of interstellar dust and gas, and entire stellar systems occasionally pass through denser regions of the galactic medium. The physics governing these interactions determines how matter cycles through the galaxy, how chemical elements get redistributed from star to star, and how conditions in one stellar system can influence others separated by vast distances. 3. I-Atlas's passage through the solar corona represented a miniature version of these galactic-scale processes, compressed into observable timescales and spatial scales. The bow shock formation, plasma heating, and chemical reactions occurred because materials with different origins, one from interstellar space and one from our Sun, suddenly found themselves occupying the same region of space. The resulting interactions showcased fundamental physics that operates wherever such collisions occur throughout the cosmos. The observations also revealed how stars affect interstellar material passing through their domains. The intense radiation, strong magnetic fields, and dense stellar winds near the Sun don't just passively illuminate passing objects, but actively transform them. Ices sublimate, grains fragment, molecules decompose, and atoms become ionized. An interstellar object leaving the inner solar system carries less mass and different chemical composition than when it arrived, having been processed by its stellar encounter. This transformation represents how stars inject energy and alter materials throughout their local environments. Future observations of stars interacting with interstellar clouds, protoplanetary disks encountering molecular cloud complexes, or stellar outflows colliding with surrounding medium would all benefit from understanding gained through 3 I-Atlas. The blue glow served as a laboratory for studying cosmic scale processes, brought close enough to examine in detail, bridging the gap between local solar system science and the vast astrophysical processes shaping galactic evolution. The lessons learned from 3 I-Atlas's blue glow transformed how astronomers would approach future interstellar visitor observations. Before this event, protocols for studying such objects focused primarily on tracking trajectories, measuring brightness variations, and capturing spectra when possible. The unexpected appearance of the blue glow during perihelion passage revealed that the most scientifically valuable phenomena might occur precisely when objects become most difficult to observe from Earth, hidden behind solar glare during their closest approaches to the Sun. New observation strategies emerged from this realization. Future interstellar visitors detected early enough would trigger coordinated campaigns involving not just Earth-based telescopes, but strategically positioned spacecraft throughout the solar system. Parker Solar Probe and Solar Orbiter proved their worth during 3 I-Atlas's perihelion, providing views impossible from Earth's location. Future missions might be designed with interstellar visitor observations as explicit secondary objectives, carrying instruments optimized for detecting and characterizing unusual emissions in the solar corona. The Vera Rubin Observatory, scheduled to begin full operations within months, would revolutionize interstellar object discovery rates. Its wide-field camera and rapid survey cadence could detect dozens or even hundreds of such visitors annually, transforming the field from studying individual rare objects to analyzing populations and statistical properties. If other interstellar visitors produced blue glows during perihelion passages, Rubin's discoveries would provide advance warning months or years before closest approach, allowing time to organize comprehensive observation campaigns. Instrument development gained new direction from the 3-eye atlas experience. The unidentified spectral lines highlighted the need for higher resolution spectrographs capable of resolving features separated by hundredths of a nanometer rather than tenths. Laboratory astrophysics programs received renewed emphasis, with calls for systematic measurement of emission spectra from exotic molecular species and rare atomic transitions that might occur only under extreme conditions. Building more complete spectroscopic databases would prevent future mysteries from persisting, simply because relevant laboratory data didn't exist. Polarimetry, which provided crucial insights into scattering processes around 3-eye atlas, would become standard rather than optional for future observations. New polarimeters optimized for faint extended sources in the presence of bright scattered sunlight would allow detailed mapping of dust and electron distributions in comet comas. Time-domain polarimetry tracking, how polarization changed over minutes to hours, would reveal dynamics of particle populations responding to varying radiation conditions. Space-based observatories gained appreciation for their unique contributions. Ground-based telescopes struggled with atmospheric absorption, scattered sunlight, and weather limitations that space platforms avoided entirely. Proposals emerged for dedicated small satellites designed specifically to monitor the solar corona for transient phenomena, positioned at gravitationally stable Lagrange points, offering continuous viewing. These spacecraft could watch for blue glows or similar unexpected emissions around any object passing near the Sun, whether interstellar visitors or conventional solar system comets. The radio astronomy community recognized opportunities they'd partially missed during 3-eye atlas's passage. More radio telescopes would be enlisted for future campaigns, monitoring for correlated bursts and mapping extended plasma structures around perihelion passing objects. Very long baseline interferometry, combining signals from telescopes across continents, or even including space-based antennas, could achieve angular resolution fine enough to resolve structure within bow shocks and emission regions. Most importantly, the scientific community developed protocols for rapid response when unexpected phenomena appeared. 3-eye atlas's blue glow emerged with little warning, requiring hasty coordination between facilities. Future procedures would enable faster instrument reconfiguration, streamlined data sharing, and coordinated observation scheduling that maximized scientific return from fleeting opportunities. Despite months of intensive observation and analysis, fundamental mysteries about the blue glow remained stubbornly unresolved. The phenomenon had been documented from multiple perspectives, characterized across the electromagnetic spectrum and analyzed by teams of experts worldwide. Yet the data gathered raised as many questions as it answered, leaving scientists with a collection of puzzles that would drive research for years to come. the most basic question persisted with uncomfortable prominence. Why did 3I Atlas produce blue emissions when other comets passing even closer to the Sun never had? The historical record was clear. Hundreds of well-observed perihelion passages showed no precedent for this phenomenon. If the blue glow resulted from natural processes involving standard physics and chemistry, those same processes should have operated at least occasionally in previous encounters. The fact that they apparently never had suggested either that 3I Atlas possessed genuinely unique properties, or that astronomers had somehow missed similar events in the past, despite extensive solar observations. The mass loss problem remained equally perplexing. Calculations consistently predicted that 3I Atlas should have lost billions of kilograms of material during perihelion passage. Yet, preliminary post-perihelion observations suggested the object emerged relatively intact. Where did all the expected ablated material go? Did it actually vaporize, but somehow remain invisible to observations? Did the nucleus have protective mechanisms that prevented the anticipated mass loss? Or were the initial size and mass estimates simply wrong, requiring revision that would cascade through every subsequent analysis? The 3 unidentified spectral lines at 462, 478, and 493 nanometers continued defying explanation. Laboratory spectroscopists had synthesized exotic molecules, calculated rare atomic transitions, and measured emission spectra from plasmas under extreme conditions. Nothing matched all 3 wavelengths simultaneously with the observed intensity ratios. Either these lines represented chemistry or physics not yet reproduced in laboratories, or they resulted from some combination of multiple overlapping transitions that happened to mimic discrete features when viewed at limited spectral resolution. The survival question loomed over all other uncertainties. Did 3I Atlas emerge from perihelion as a coherent object? Or did it fragment into multiple pieces hidden behind the Sun during the observational blackout? Comets occasionally break apart when stressed by heating or tidal forces, creating families of smaller fragments following similar trajectories. The blue glow might have masked such fragmentation, with emissions from multiple pieces blending together into a single apparent source. Only continued observations as the object emerged fully from solar glare would reveal whether one large nucleus or several smaller fragments now traveled back toward interstellar space. The bow shock structure raised questions about plasma physics in extreme environments. The sustained emission over days implied continuous energy input far exceeding what simple models predicted. Where did this energy come from? How efficiently could shock processes convert orbital kinetic energy into particle acceleration and heating? The observations pushed against the edges of theoretical understanding, revealing phenomena that existing models struggled to explain quantitatively, even if they captured the basic physics qualitatively. Most troubling was the possibility that the blue glow represented only one aspect of 3I Atlas's unusual behavior. What other surprises might emerge as the object continued its journey? Would post-perihelion observations reveal additional anomalies? Or would the interstellar visitor gradually settle into more conventional comet-like behavior as it moved away from the Sun's intense influence? The months ahead would determine whether the blue glow represented an isolated curiosity or the first hint of deeper mysteries yet to be uncovered. As 3I Atlas emerged from behind the Sun in late November of 2025 and continued its journey back toward interstellar space. The blue glow gradually faded from view. The intense radiation environment that had triggered the phenomenon weakened as distance increased, and the exotic emissions that had captivated astronomers for weeks diminished below detection thresholds. What remained was archived data, terabytes of images and spectra captured during those extraordinary days when an interstellar visitor revealed properties that challenged fundamental assumptions about how matter behaves near stars. The blue glow left behind more than just scientific puzzles. It transformed how researchers thought about the boundary between stellar systems and the vast spaces that separate them. 3I Atlas carried material forged in an alien solar system, preserved through millions of years of interstellar travel, then suddenly subjected to our sun's intense scrutiny. The resulting interaction showcased physics operating at extremes rarely observed, creating a natural laboratory that illuminated processes relevant across multiple fields, from solar physics to astrochemistry to plasma dynamics. Whatever 3I Atlas truly represented, whether a massive natural comet with exotic composition, a fragment of planetary debris with unusual properties, or something even more extraordinary, it had succeeded in expanding human knowledge in unexpected directions. The phenomenon forced scientists to confront gaps in theoretical understanding, develop new observational techniques, and collaborate across disciplines in ways that advanced multiple research fronts simultaneously. The blue glow served as a reminder that the universe still held surprises, that even phenomena as seemingly familiar as comets could behave in ways that violated expectations. The legacy would extend far into the future. Every subsequent interstellar visitor would be studied with protocols refined through 3I Atlas observations. The spectroscopic databases would grow to include emissions documented during the blue glow event, providing reference data for identifying similar features if they appeared again. The plasma physics models would incorporate lessons learned about ball shock formation and particle acceleration in extreme environments. The observational networks would be better prepared to coordinate comprehensive campaigns when the next opportunity arose. But perhaps the most profound impact came from demonstrating that genuine mysteries still existed in accessible regions of space. 3I Atlas didn't require voyages to distant galaxies or exotic extreme environments like neutron star surfaces. It brought frontier astrophysics to within a fraction of an astronomical unit from Earth, close enough to study in extraordinary detail, yet strange enough to defy complete explanation. This accessibility made the mystery more tantalizing, more immediate, more real than theoretical puzzles about phenomena billions of light years away. As the interstellar visitor continued outward, gradually cooling and fading as solar heating diminished, it carried with it secrets that might never be fully revealed. The blue glow represented just one chapter in 3I Atlas's story, a brief interaction with our sun that illuminated both what we know and what we don't about the cosmos. The silent giant had spoken through light and radiation, leaving messages encoded in spectra and images for scientists to decipher for years to come. Whether those messages would ultimately reveal revolutionary new physics, confirm exotic but natural chemistry, or simply expose gaps in current understanding remained to be seen. But the impact was already clear. 3I Atlas had shown that the space between stars was not empty wasteland, but rather a dynamic frontier carrying materials and information between stellar systems. And that studying these messengers from interstellar space offered windows into cosmic processes operating throughout the galaxy. The blue glow had faded, but its legacy would illuminate astronomy for decades to come.